I think we're recording right now. Hopefully it goes through. Sometimes it doesn't, but anyway, we'll see how it goes. Can you still see the recording sign up now?
Yeah.
Yeah, great. Okay. So I guess, yeah, so again, it's up to you what we want to cover. I was thinking if we had 2 hours, we'd cover analog to digital conversion, the second half of that, digital bandpass transmission, and a little bit of digital noise. But it's up to you if you want to maybe focus on more past papers or some sort of tutorial question. Let me know.
Yeah, that's not a bad idea. I really don't know. Like, I would prefer doing past papers, but then since they've changed the way they set the papers, I don't know if that's a good idea. Because I prepared with the past papers, and then the actual the paper that they said was just completely different.
Yeah. Okay. So which past papers are you talking about? 2005, 2006, or the more recent ones?
Even the most recent ones, because the online exam is much more theoretical based, so they don't set the easy questions anymore.
Yeah. So would you want to look through maybe, I think, what do you have access to? Because I have access to 2017 and 2018 and also 2013. Do you think those would be better?
I'll quickly check because I haven't checked what past papers I have right now.
Yeah. Because what we could do, because actually I don't know if there's solutions to those, the 2017 and the 2018 papers, which we could just probably email the course coordinator for those, but we could also work through and start making solutions for those as well. We could use this time to do that.
Yeah, she hasn't given papers yet. I remember from last time there was 2018, 2019 with solutions, and then the older ones they didn't have any.
Okay, so do you want to work through maybe some of those, like maybe 2005 or 2006? I've got.
Yeah, I don't mind that.
Oh no, 2005 and 6 that they have solutions. We can still work through them if you want, but I've got solutions for those. I think they're on the ELSOC website.
Either one's fine.
Okay, so let's maybe have a skim through because they're both 3-hour-long exams, so we can just have a look through and then see if there's any sort of any questions that you'd like to go through. So I'll post them in the files. Okay, great. So can you see those in the chat now?
So are they in the chat or in the files?
It's in the chat, actually, the meeting chat.
Yeah, I don't really know my way around this that well.
Yeah, so if you look down the bottom, it says show conversation in the bar. And if you click on that button, it should show you the meeting chat. Hello, Ruben. Can you hear us?
Yeah, mate.
Hey, how are you?
Oh yeah, could be worse. How's things?
Were you looking to stay for this crash course?
Yeah, I'm doing tele.
Yeah, cool.
Last time.
Because we have two options. We were gonna do. I've got a crash course prepared that goes through the entire course, but then I thought it was just going to be with here, so we're just going to go through some past papers. But if you want, we could still just go through the course and get a bit of a summary of that. Because the past papers we were going to do, they have solutions anyway, and I feel a bit redundant going through those questions if there's solutions to them.
Yeah, I don't know. I'm happy to go through the past papers, but are you going to upload the crash course thing later?
No, it's more, I think we got some good feedback from this term being like, can you actually make slides so we can go through this stuff later, because usually I just write it down. So yeah, so I've got like my notes,
Yeah,
but they're not publishable.
fair enough. I don't know. I haven't actually finished the lectures, so
Yeah, cool. Yeah, so we'll try going through some papers. So can you access the chat
yeah, I'm looking at it
at
now.
all? Cool. Okay, great. So I'll just share my screen again, just so we have it on the recording. But yeah, I guess we'll go through this. Okay. And Wasik, can you access the papers yet? Did you find the chat bar or?
Yeah, I
Yeah,
have the
cool.
2005 open.
Yeah, perfect. Okay. So question 1 looks to be just an amplitude modulation question. I think that looks pretty straightforward. Part B. Okay, so part B is amplitude modulation via a squarer. That's something we haven't probably covered in labs. And then question 2A. Yep, so double sideband suppressed. I'm pretty sure Ruben, did we cover this in the labs? Was this the same setup?
Okay. Yep, that's better.
Cool.
Covering DSBSC.
Yeah, I'm pretty sure we have had a similar setup with
Yeah.
what was it called? It was like a split phase or something. Where we add the 2. Okay, filter output. Okay, so question 3, we had the Hilbert transform. So that's, I guess, a little bit interesting. We've probably done that in the lectures, but super heterodyne receiver. Are you guys? Are you familiar with super heterodyne receivers?
To a basic extent, yes.
Awesome. That's really important. Usually there are questions on that. Ruben, you're good with that as well, or?
Oh, near enough.
Near enough. Okay, make sure you revise super heterodyne. It's really important, and super heterodyne covers the 2 sort of ways of coherent detection and envelope detection. So yeah, it's really good to revise that part. Great, does a bit of vestigial, and then question 4, we look at FM, instantaneous frequency and frequency deviation, and then phase lock loop demodulation, and then some bandwidths. These are really good questions, actually. They're really good for revision, I'd say. Okay, then question 5, we have time division multiplexing. So this is interesting. This is stuff we probably wouldn't have covered since the midsem. We have a PCM signal noise ratio. Yep. An information theory question. So this is really good stuff. I'm not sure what you guys are thinking, but I think going through question 5 would be quite useful. And then, yeah, line coding, phase shift keying. Ruben, so what lectures have you gotten up to?
Everything except I'm halfway through the second last one.
Yep, and what was that covering?
You can tell I remember them a lot.
Yeah, right. So is that transmission maybe, like multiplexing information theory, or
Digital
was that
noise.
back in digital noise? Oh, perfect. Okay, so yeah, so you should have most of the stuff. I'm not really. There's not much I've got to say on digital noise. Like it's a bit wishy-washy. I think that last bit, like most of it, like they do ask questions about it, but most of it is actually in analog noise.
Yeah.
And there's a little bit on matched filters and pulse shaping, but yeah, I find that TELE's a hard course because it's hard to know what is accessible and what isn't. Okay. Yeah, so we bit error probability, and then we look at the bandwidth. Yeah, and we do look at a Nyquist filtering technique in part H. So yeah, so I think we can probably choose, but I think a lot of question 5 would be really useful to go through. What do you two think about that?
Yeah, that sounds good.
Yeah, it wasn't covered in the mid-sem, most of that.
Great. And usually, if this were an exam, we'd probably want 30 minutes for this section. So hopefully we should be able to cover it. Okay, and I'll just quickly stop over to 2006. And also, even if there was stuff we covered in the mid-sem, if you guys are really, if you're feeling a little bit shaky on like frequency modulation, or I remember last time we went through some of those questions that you were feeling, not up to scratch on. So definitely, it doesn't matter if it's like the first lecture. If you want us to go through something, let's do that.
For me, it's most of the second half, like the analog to digital and all that. That's something I'm not fully clear on.
Perfect, great. So that question 5 should cover that well. So I've just moved on to 2006. Question 1, amplitude modulation. Oh, another square law modulator. I hope 2006 isn't just 2005 rehash. It probably is.
Typical.
Yeah, and there again, Weaver's method for a single sideband. FM with phase lock loop. Okay, question 3 is interesting. Question 3 is all about noise. And noise that was always my weakest part. I don't know about you two, but it's talking about added white Gaussian noise and the signal noise ratio and figure of merit, that sort of stuff. So if you're cool with that, we can move on, but that might be something we want to look at with Seek and Ruben.
I kind of know how noise works, but I just can't derive the relationships.
Okay, yeah. What, so you can't remember them, or you don't know what they mean, or you can't?
Yeah, I just kind of just trip over how the relationships are going to come together, especially if they're not exactly like the ones that are shown in the lecture slides.
Yeah, and especially with I find that in noise that they throw a lot of different things at you in terms of like figure of merit, etc. Okay, so question 3, we may go through that. We'll have a look at question 4 and 5, and we'll see if they're a little bit better. Question 4. Okay, we look at pulse code modulation, aliasing, spectrum, bandwidth. Time division multiplexing, frequency division multiplexing. Yeah, so I guess that's a little bit. That's okay. And then question 5, delta modulation, binary phase shift keying, symbol entropy, Hamming, eye diagram. Okay, so what do you think? So we might choose, if we should roughly spend about half an hour on each, we might go through 3 questions. So I think 2005 question 5 looked good, and maybe 2006 question 5, but then maybe we'll just choose one between question 4 or question 3 in 2006. Or what do you think, Ruben? Do you have any preferences with what questions we go over, or would you prefer? I can also go through, if you want, maybe we'll cover 2 questions, and if you want, I could condense the overview into half an hour. Like it's completely up to you guys what we do.
Yeah, I think that might be useful. Just a bit of overview would be handy as well.
Okay, would you want to start with the overview or finish with that?
I'm not fussed. We'll Seek.
Okay.
On.
Yeah, we'll Seek.
Yeah, I'm happy with that.
Happy with what?
Just half an hour overview, and then we can just do questions.
Cool. And then out of paper 2006, do we think question 3, question 4, or question 5?
Either one's fine. I really can't tell which one's better.
Okay, cool. I think we'll go with question 5. I think it looks a bit harder, but again, if you see anything, let me know. Cool. Okay, so okay, perfect. So first we'll start with analog to digital conversion. So Ruben, what are the steps once we have an analog signal? How do we convert that to something digital?
So we just sample it at regular intervals and then quantize it and store it.
And why do we have to quantize?
Because we'd have to save it as a binary value in some certain number of bits.
And why can't we just do that with the sampled?
Because the sampled value will not take those discrete values.
Yeah, great. So we have a set of discrete values, and then we encode them into some sort of, we use symbols. Okay. And then we send them down a line. Okay. Great. And then so we'll seek what's the error that comes across with quantization. If I say, let's have these quantization levels, and we define the delta as 2 Vmax on the amount of levels. What would be the average error between these quantizations?
Not too sure.
Okay, Ruben, any idea?
So the average would be half of the spacing between the levels.
Yep, cool.
Oh no, that's the maximum error.
Yep, so error is usually within, so it's plus or minus delta on 2. Okay. And then if we do the power, I won't go through the derivation, but essentially what we're doing is we're integrating, and I think it comes out to delta squared on 12.
Yep.
Okay, and then how do we work out then the signal to noise ratio? What's the basic formula for signal to noise?
Well, power of the signal on power of the noise.
Right. Yeah. Okay. So power, and then we usually express that in something log. Is it 10 log or 20 log?
For power, it'd be 10.
Perfect. Okay, that makes sense to you. We're sick. So we have the power of the signal and the power of the noise. Okay.
Yeah.
And we know that the power of the noise is this delta squared on 12. Okay, and we also sub that delta. I'll just draw a lasso around this, bring it down. We also know that delta is 2 Vm on L. So we sub those 2 parts in there. And then we get this big equation. I think it's 10 log PS on, I think it's like Vm squared on 3L squared once it all sort of works out. And then that expands. And usually I never recommend learning the expansion, because why would you? Like, just derive it. It's really quick. So it's around 5 plus 20 log L minus 10 log Vm squared on power signal. Okay. But Ruben, so what's the signal noise ratio? What's it proportional to? So as you increase or decrease L, what happens, and why is that?
So the signal noise ratio, as you increase L, should decrease, because there's less of a difference between the potential analog values and the quantized values.
And what, so you're saying it's a better signal noise or a worse signal noise?
The signal to noise ratio is higher. That means you're getting a better signal. Perfect. When you have more levels.
Yeah. It's just confused me when you said low for a minute. Great. Okay, so it's proportional to L. So the bigger the L, it means there's less error. And we can see that mathematically, because SNR is 20 log L. So as L increases, log L increases, etc. We'll seek. What about Vm? So so VM here is just the height. So that's VM, and here is 2 VM. So this is like the peak to peak of our values.
I think like from the relation,
Yeah.
increasing the VM would decrease the SNR, so signal would get
Perfect.
poor. And
Yep.
I'd imagine like physically as well, because there's a bigger error that can come in when you quantize it. So
Great.
the
Okay.
error
Because
rate increases.
yeah, essentially, if we're trying to quantize, a larger signal, it means we're going to have less dynamic range because our levels will be spread out more. I say 1 on VM here. That's just my way of writing less, like it's not exactly inversely proportional, etc. Just keep that in mind. And of course, it's going to be proportional to the power of the signal, of course. Great. Okay. So the next thing we'll go through is pulse code modulation. Okay. Okay, so I'll just write here. So we have, the first sort of method of coding is pulse code modulation. Ruben, can you remember what this was roughly about?
Pulse code modulation. So you express the value of the analog signal in terms of either the pulse length, the pulse amplitude, or the pulse position.
Yep, cool. So that was yeah, no, that's right. So yeah, so that's pulse amplitude modulation, pulse width modulation. But the step before that is just how we encode it. So right now I've written down some values. So first, if we sample a signal, so we get something like 3.6, blah, 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 we then quantize that to a level, which might be 4. And then what we need to do that is we need to encode that, okay? So we need to encode it to whatever, and I'll write in brackets here, it's symbol, okay? So let's say we have, the 4th level, let's say it's the 6th symbol, okay? And then we have to somehow turn that code into bits, okay? So we can write 6 as 110, okay? Or we could write it as 111 if we were looking at gray code, okay? And why do we use gray code, and do you have a way of remembering how to make a gray code table?
Gray code, as far as I know, it's more resistant to noise because only 1 bit changes at a time. So you can kind of tell that there's error happening if there's 2 bits changing.
Yeah.
I don't really have a way of remembering the table though. I just keep in mind that only 1 bit has to change each time.
Yeah. Okay. So very simple ways. So you can start off. So for 1 bit gray code, we'll just write 101 as normal. And there's 2 steps we do. So the first thing we do is flip it. So we say, for 2-bit gray code, we go 01, and then we write 10. Okay. And we also write 0011. So then for our 3rd bit of gray code, we flip this entire part. So we have 000110. 1110. Okay, we flip it. So 1011, 0100. And then again, we add 00001111. Okay, and that continues. So do you want me to keep going? Do you understand the flipping and adding process so far?
Yep.
Great. I found that's a really good algorithm just from like Wikipedia of how to generate gray code. And as you said, the 1-bit change, you can get errors. And also, if you think about it, I've got a low Apple. With something like, amplitude in here, we're quantizing and we're making the symbols. But if we have an error, let's say we quantize it at 1 volt levels, right? And this is level 4. If we have an error, that 4 is either going to be a 5 or a 3. It's only going to change by 1, right? Whereas if 2 bits changed, saying going from 111 to 000 or something like that, we might jump from 4 volts to something like -1 volts. There'd be a very large jump in the D coded symbol. So you're right when you say error. It's really easy to pick up errors, but it also means that if there are errors, even if you don't fix them, they only have a minor effect. Does that make sense?
So as
Oh, no, not really.
so as in the effect of error is minimized pretty much.
Minimized, perfect, great. Okay, so it means that like instead of if one bit changes, your voltage level is just going to go to the next one up or the next one down. It won't jump around wildly. Okay, so another bit thing to remember is the amount of codes n, the amount of bits. Okay, is just log 2 of however many levels we have. So if we have 4 levels, we'll need 2 bits, etc., etc. And that sort of that brings this compromise, right? Because as we know with our signal noise ratio, we can't really control the input voltage of our signal. So the only thing we can really control is the amount of levels. But the more levels we have, the more bits. Okay, so that's a big sort of compromise in there. I'm just going to shift this one down a little bit.
Question, Tim.
Yep.
For your PWM, PAM,
Yep.
PW, the other one.
PPM. Yep.
Yep. Do those need to be quantized values? Because couldn't you have any amplitude or any width
Yep.
of your pulse?
Yep. Yep. I guess, yeah, so I guess if there was an analog way of converting whatever your sampled voltage level was to your pulse position, because yeah, position, width, height, they're all continuous values. So yeah, it definitely doesn't have to be quantized. But if it was a digital system where there's a step in between, you'd have to, there'd be some resolution on, you know, how many decimal places do you measure your sampled thing to, you know, at 3.614 or 3.61472. So yeah, but if it's a purely analog system, which I'm not sure if they really exist, I guess in our labs, what we had is when we had our signal here, what we did is we used sort of natural sampling.
Yeah, but that creates
and that would be, yeah, but that would be an example of where it wasn't actually quantized. So yeah, so I guess, yeah, and the example of this would be a sample and hold. Okay, because that's where you sample it and then you put it through an RC or just any sort of capacitive network to hold that level until it next gets pushed up again. And that would be, because it's analog, that wouldn't have any quantization in it. Does that answer your question?
Yeah, thanks.
Perfect. Okay, and so the second mode we have is delta modulation. So Ruben, what is delta modulation and why do we use it?
I'll have to look at my notes, but
yeah, that's okay. Wasim,
remember.
Can you remember?
I don't understand delta modulation at all. I really don't know about it.
Okay, so pulse code modulation.
Ah, yes, delta modulation. I'll remember now.
Yeah, cool. Yeah.
It's where you don't modulate the actual value of the analog signal. You modulate the change in value of the analog signal from the previous value.
Perfect. Okay. Great. So in our pulse code modulation, you know, we've got this sort of signal here. It sort of just follows, you know, our signal wherever. But why do we have to do that, right? Because usually for most of our signals, they're not jumping, you know, like 2 steps up, two quantization levels up, or maybe, you know, 5 quantizations down very, very quickly. Okay, so usually that's increasing or decreasing by 1. So why can't we just encode if there's any sort of change or if there's no change? And of course, Ruben, where does that break down, that theory?
You in there, Joe?
When you do have dodgy steep things.
Yeah. Okay, so there's always going to be a limit, and that limit is determined by the size. So that delta, that size, and that's where we get adaptive delta modulation. Okay, and essentially what that says is instead of having this red line, what we do is as soon as we have a couple of bits in a row, we start increasing the size of the delta until we've hit it again. Okay, and you're like, oh, well, how can we do that? How is that going to make demodulation happen? But so this would give us a string of zeros. So we'd have 0, 0, 0, until we finally get a 1, you know, when it sort of catches up to it, the curve, okay? And that means on the demodulation side, when we're trying to recreate this signal, so I'll again draw it, we'll have a 0, 0, 0, 1. Every time we have a 0, the size of the recreation increases until we get a 1, okay? And then we pass it through a low pass filter, and hopefully we should get to our normal signal again. Does that make sense, Wasik?
One quick question: what limits how quickly the delta modulation, basically how much change the delta can adapt to?
In the adaptive delta modulation?
In general, because you know how there's a certain rate of change at which delta modulation just cannot keep up. What's determining that limit?
That limit is determined by the designer. So there's two things, because essentially we're talking about slope. So I guess if we're looking at the signal, we look at both the width, okay, so the sampling rate, so fs, and we also look at the height, okay, and that's delta. Okay, so if we have a very big height, a very big delta, it means that we can have a bigger slope, but it also means that we won't have such fine resolution, I guess, around the smaller curves, right? So if we want really high resolution, which I'll draw over here to the left, we'd want, you know, very small deltas, okay, to capture that. And if we want a very large resolution, we'd have to get very large deltas, okay? So you've got to choose one or the other, or go the adaptive delta modulation route. But the adaptive one, of course, is harder to implement. And this is a very big caveat here. Use my rainbow pen. Is that you should look up implementation. Okay. No, I don't like rainbow pen. Okay, this is in your lecture notes. It's pretty similar to what I've drawn up the top up here, but essentially, yeah, each of, you know, the pulse code modulation and the delta modulation have implementations. You're never really asked about them. You could be, but it's good just to get an idea of, you know, the different steps. So if I wanted an adaptive delta modulation, because it's slowly increasing and decreasing, there might be some sort of integrative element. Okay, and the last modulation we have is differential. Okay, so differential modulation is just, okay, instead of using the delta, why not? So if we have a signal here, right, and let's say we're sampling it at different points. Okay, so if I have two different points next to each other, let's say I can predict where it's going to be next. Okay, so I draw that little line of prediction. Okay, and at the next sampling point up here, I'm going to measure these 2 points, what my predicted point would be and what the actual point would be. And I measure that, okay, and that's going to be our prediction error. Okay, and then we modulate this, okay? So we pass that number, you know, let's say 0.45 something. Then we, you know, encode that into bits and we transfer that, you know, in PAM, PPM, etc. Does that make sense? Okay, so, and that means on the demodulation side, we need a predictor. So essentially with all these modulations, we just need the inverse of the modulation side to demodulate it.
I'm not fully sure if I understand the prediction error part. Like,
yeah. Can you think of why that would be useful, or where it'd fail?
No, as in, I don't really understand how it's working basically.
Yep. So essentially what you'd have is you'd have some sort of predictor. So that might be, you could think of a low pass filter, right? So if a low pass filter was, let's say, given this signal, okay, and then it was given, and then that signal went to 0, okay, the actual output of the low pass filter, it would be following this, and then here, it would take a while for it to go back to 0, right? So the capacitor, the RC network, okay, the capacitor is charged, so it's going to slowly discharge. So in a way, what we're saying it's doing is it's predicting, or it's continuing whatever the previous signal was. Does that make sense?
Yeah.
Okay, so then what we do is we measure this height, so the height between whatever the prediction is and what reality is, and then we transmit that through our line code. And of course, in this case, it's, you know, it's this really big value, but usually it's not really big value, because usually, we'll get into this a little bit later, but usually our signals are correlated. So instead of having that big drop off, it might, you know, duck down a little bit, okay? And that means that we can actually get quite high. So I'll make a note of it here, quite high dynamic range. Okay, because it's always measuring this, it's not some sort of delta where, you know, in delta modulation, if you have one of the things that's wrong with it is if you have, let's say, this small varying line, your delta is going to be constantly going up and down, up and down. It's introducing all this noise and error. Okay, so to get rid of that, if we were doing differential modulation, if it wasn't changing that much, then our prediction would also not be changing that much. So that means we wouldn't have to transmit so much information, and we actually get quite good dynamic range. So it's actually, it's quite accurate to our signal. Does that make sense? Why those two are different?
Kind of. I'm just sort of trying to understand how this would be implemented.
Yeah. So I'll just check the lecture notes on that.
Would they have like an identical RC filter
On the other half,
at the
yeah.
demodulator?
Perfect, yeah. So they have an identical RC at the demodulation side. So capacitor, resistor, okay. And then what they do is that is making whatever the prediction is. And then what they do is they add to that whatever that error was that we've measured before. So this error over here, we pass that in there, and that means that we'll actually get our identical signal, the output. So that addition, you know, we might have an op amp or something like that to perform that addition.
Yeah.
And that's why I mean to say, when we look at the implementations of all these systems, it's actually really easy, because the demodulation is just the modulation inverted. Okay, so differential. Okay, so what I'm going to do is I'm going to, or do you have your lecture notes in front of you, Ruben or Wasik?
I can open them now.
Honestly, don't remember learning about this.
Yeah, well, I'm sure. I'm actually not sure if you have the same. Do you have the same lecture notes this year as last year? Wasik.
They did from last semester. They did change a couple slides. They added a few annotations as well.
Oh well, I hope I hope this is in scope. Maybe you didn't learn about it. That'd be awkward.
Like last semester, they went over it very briefly, so it was just not something that was covered that well. I don't know how it went this time because
Yeah.
I'm not up to speed with the lectures.
Yeah, cool. I'm just gonna post it in the chat. Where are we?
This is DPCM, is its acronym?
Yeah, awesome. Yeah, so it should be around page 40 of those notes. So you see DPCM, it goes through a little bit, but it goes to the transmitter and the receiver, and you can see they just say, they don't even say, they just say it's a prediction filter. But I don't even know if they say what that could be. So maybe Wikipedia would be a good one to look that up. But yeah, and you can see that it goes through that prediction filter, but there's some sort of delay, and it gets added again. Yep. Cool. Okay. So yes, so that's our part. Okay, and the last thing, we won't really cover this, but because we'll do this in the, and you've done this in labs heaps too. I just get rid of that. So just how do we implement these? So as we said before, there was, you know, PAM, PPM. I'm actually not sure why you use that over line code. I think line code is subtly different. Okay, so what we're doing is we're taking these 3 different types of modulations. Okay, and what we do is we transform that into line code. Okay, so I don't think I'll cover those because I'm sure we've done them to death in the labs.
What do you
but
mean
we
when you
have-
say line code?
Yeah, so those are the unipolar,
Oh, okay, yep. That makes sense.
polar. But what I will cover, and what we'll talk about is, so what are the advantages or disadvantages or pros and cons? Ruben, what do you think bandwidth is related to when we're talking about line codes?
Just the number of switching quads. So if they return to 0, you have to switch again in the middle. And that'll have a higher bandwidth.
Why is that?
Not sure exactly.
Okay, so if we think about, or Wasik, do you have anything to add on this? Do you know what's influenced the bandwidth of these signals?
I think it was the bit rate, especially with the return to 0 ones, because I thought you would be using 2 bits, one for the previous part and then the one for the second half of the signal where it's returning to 0.
Yep, great. Okay, and both the things you're talking about, they're actually related to just the width of the pulses. Okay, so when we learnt about our square pulse, right? So this is the time domain. When we go into the frequency domain, what's the Fourier transform of a square wave or a pulse?
Sync.
Sync. Okay, and how are they related? So if I have a very narrow, so if I decrease the width, what happens to the bandwidth?
If you decrease the width, the bandwidth should get wider.
Wider, right? Okay, so, and essentially a couple ways of thinking about that. Essentially, if you want a smaller width, right, it's almost like you have faster transitions, and that means you need a higher frequency. Or you can think about the period. So as the period decreases, the frequency increases, so you need a larger bandwidth. And you can kind of you can also think about impulses and DC lines, like something that's DC, it's not changing. It is a very small bandwidth that only has one spike at 0, and an impulse, which has an infinitely small width in the time domain, has a infinitely wide bandwidth. There's a bandwidth of 1. Okay, so I'll just draw these in here. So an impulse has a infinite frequency. Okay, and a DC line has a 0 hertz. So
Just
one
a quick
component.
question.
Yep.
I remember going over this in the lectures briefly,
Yeah,
that
yep.
we don't use proper impulses because they make the signal a bit unstable.
Yeah.
Is there any place where they actually use impulses, or is it always pulses?
No, because you can't have an impulse. So the definition of an impulse is something that's infinitely tall and infinitely the width is infinitely small. So of course we can never generate something like that. So all we can do is get a very, very small and high pulse, right? And that's really hard to make, actually. And you'll find if you ever go to the basement of the electrical building in the high power, the high voltage lab, they have pulse generators there to make these very large pulses, and the reason why we use it is we use them to characterize our transfer functions of systems. Okay, so we pass it through, and the reason why we want to do that is we want to pass through all frequencies at once. But as you said, for a very small width, we'll have a very large bandwidth, but it'll still be a sync function. Okay, but we want to do that because we want to test over a large range of frequencies whatever our transfer function is, right? Because our transfer function, we always say it goes off into infinity, but really you can never check that unless the input signal you apply to it has an infinite bandwidth. Does that make sense? Because you're convolving them in the time domain and you're multiplying them in the frequency domain.
Yeah, it kind of does, yeah.
Cool. There's a lot of stuff all at one time. So basically bandwidth is proportional to the time. So something like bipolar, where we have these short pulses, is going to have a larger bandwidth. And as you said before, as the data rate increases, so this is a signal with a low data rate, and this might be one with a high data rate. Okay. So more bits per second equals more bandwidth, because they're narrower pulses, okay? And that's why with things like 4G or fiber optics, we're always looking for larger bandwidth systems. We're not going to get faster signals like your ping or lag doesn't change because you're only capped by the speed of light, but we can put more bits in per second, and it's that bandwidth that allows us to have what we call a fast internet connection, but it's not actually really fast. It's just high throughput, high bandwidth. Okay. Other advantages, disadvantages are more basic. So I guess just like complexity, inversion is a big one. Okay, so that's if we flip them as we did in the labs, which can be recovered, which can't. Usually things like Manchester or bipolar are more are better in terms of inversion. And the last thing is timing. Okay, and with timing, what I like to say is if you had a long string of like 0, 0, 0, 0, 0, for something like unipolar, that would just give you a flat line. Okay, and that's bad, obviously, because you'd lose the timing on that. Whereas something like, I'm not sure actually, maybe Manchester, I don't know. But there's ones where even if it's 0, 0, 0, 0, it'll always change. It'll still change, and it's sort of the direction of the changes. Okay, and that will always have timing information.
Well, on your
but
RZ codes, don't they have timing information?
Yeah, but mainly just focus on, but what happens if you pass in a long string of zeros or a long string of ones? Because usually if you have like a random data stream, all line codes contain timing information, but especially if you have those long stretches, you can get timing errors because you might have a long string of zeros or a long string of ones, and then if it's not changing, you'll lose that timing. Okay, cool. It's 4, but we'll squeeze in the last little bit. So are we happy to keep on going, or do we want to switch over to do some questions now?
I think this is good.
Well, Seek, how are you feeling?
We can go over a bit more theory. I'm just really not sure about this section, so I welcome the theory.
Cool. Okay, great. Well, yeah, and as I said, the past papers do have solutions. And that's all I'm going to be running through with you. So just keep that in mind, and I'll give you guys those solutions after we're done the session. So you can go through those on your own time as well. So this was, so we're already through. So this was, pretty sure this was only 1 week. Okay. So the last 2 things we want to look at, well, there's 3 things actually. So digital modulation, transmission, and also digital noise. Okay. So what I'm going to do is I'm going to scroll down here. I'm going to start a new page. I don't know how I feel about whiteboards. How's it going? Are you watching the recording, or do you have the whiteboard open and you're looking at that? I think Ruben, you're on the whiteboard, but Wasik isn't.
I'm looking at the whiteboard. I don't know if I can edit it.
Yeah, cool. So you can also, if it helps, back, not in the call, or I can also, I can probably share it.
Okay, I can draw. Cool.
In there as well. Yeah, so you can, it's more, but the resolution is just better than because I'm screen sharing right now, so it yeah, so the resolution isn't that great. We'll see, can you click that link, the Microsoft whiteboard I've just posted in the chat? And it's also in the main TELE3113 chat as well. So just click on that. You might need to sign in, but yeah, that'll put you through there. Okay, so let's go through. So we've got digital modulation.
Sorry, Tim.
Okay.
I think I missed an advantage of that line codes could have. You said there was inversion properties, timing. Yep. Was there something else? Bandwidth. Yeah.
And complexity.
Oh, yeah. Okay, thanks.
So that's complexity of modulation. I'm sure. Well, actually, yeah. While we're here, can you think of any more ways to compare different line codes against each other? Because I think we've gone through them in labs, and this is all. I always like to ask people, like, why would you choose, unipolar over polar, and all these factors sort of come into play. And like complexity, usually that has to do with phase lock, or also, you know, with unipolar and something like bipolar, you need more sort of power supplies or voltage levels.
Yeah, that's what I was going to say. The bipolar.
Cool. Okay, so digital modulation. As we've gone through, so, you know, I'm definitely coming back to these steps right at the top. So we get our analog signal, we sample it, we quantize it, we encode it. But then what do we do once we have that encoding? Okay, so
Hey
once
Tim,
we've got, yep.
sorry to interrupt. Do you mind if I just leave for like 5 minutes?
Yeah,
My
you gotta
mark
do
is
marking.
getting ready to mark. Yeah.
Ruben, are you okay if we wait for 5 minutes?
Yeah, sure.
Cool.
Thanks.
Yeah, so Ruben, while we're here, is there anything you want me to go over, you know, what we've gone through so far, or even stuff from before the mid-sem that you're not feeling as sure about?
I never really understood phase lock loops.
Cool, great. Yep, that's a really, I like going through that one because that's one that I didn't really get going. So I have this little bit at the top here. Okay. Okay, and I'm just going to look up, I've got it written down the way I like to explain this. How do you usually think about phase lock loops?
Not since the midsem.
Yeah, okay. If you had to explain it to someone else, how would you explain it to them?
No idea. I don't know how I got through the midsem.
Okay, so first, let's think. How do we generate FM? What are some ways of generating FM?
Well, there's your narrowband, which you basically use the first term of the Fourier transform of your signal wave.
Cool. And there's like Armstrong's method for making narrowband into wideband FM. I'm pretty sure.
Yeah, I've read that.
And another way is also using a voltage-controlled oscillator.
Yeah.
So we've got a message of T, we pass that through a VCO. Okay, and then it goes through our transmission line. Okay, so essentially our message, we'll write our message here. Okay, and so our VCO, what that does is, you know, when it's high, we have, let's say, a high frequency, and then when it's low, we have a low frequency. And you remember from the labs that there were two parameters we changed of these VCO. Can you remember what those were?
You're pushing me.
So a voltage controlled oscillator, what do you think? What's a parameter
so there's
you
your
might have to tune
voltage gain and your amplitude.
Yeah. So there's a sensitivity beta, the amplitude, great. So that's usually fixed. And there's also what we call, I'll just call it omega naught. Okay, because usually when we oscillate, we don't oscillate from DC, but we have some base frequency, like let's say 10 kilohertz, and then depending on beta, we'll go above and below. So we might go up to, you know, 11 down to 9 kilohertz, depending on the input voltage level.
Yeah.
Right. Okay. So those are the two parameters we changed on that. So here, you know, in the middle, so when we have a 0 voltage here, that might give us maybe, let's say 10 kilohertz. And at our maybe 1 volt here, we'll get, let's say 11 kilohertz. And at our negative 1 volt there, we give 9 kilohertz. Okay, so the we have frequency modulation, okay, essentially. And what we do to demodulate that, essentially, we use something that we call a comparator. Okay, and what can you think? So how can we compare two signals? What we want to do is we want to have two signals. So we want our FM okay, and some, random signal. And we want to compare them and see, how similar or how different they are. What could you think of ways of comparing these two signals?
Comparing the instantaneous value of them.
Yep.
Which two of those signals? Are they the LPF and the message?
Let's just say these in red, signal 1, signal 2, just random signals.
Oh, okay. Well, you could just use a comparator, your op amp kind of thing.
Op amp, great. Yeah, op amp is one. Okay, a multiplier is another one. Because if it multiplies by 0, etc. And the third one, I think, could be like I think it's an XOR gate. Okay, so there's a couple of different ways of doing this, but essentially we just want to compare the two signals. And if what we want to do is we want to pass through, so if they're exactly the same, okay, it's just going to give us, what's the best way of explaining this? Okay, great. So what we'll do here is, so let's just, instead of looking at a time, let's just look at two different, so there's one point in time, we have these two different voltage levels. Okay, so what we're going to do is we're going to pass through that delta V, okay, that change in voltage level, and we're going to pass that into the low pass filter. So of course, that delta V will be changing through time.
Yep.
Okay, so let's say it's like that. We pass it through the low pass filter, which is going to smooth it. And then we pass that blue signal into our voltage controlled oscillator. And like with FM, the voltage controlled oscillator, in terms of this signal, so we'll just draw here. So it's going to be high frequency for this part and then low frequency for the low part, right?
Yep.
And at the point where it's 0, it's going to be just dead on whatever the base frequency is. Okay, but you can see what we're doing now is we're generating another FM signal, right? So we're inputting to the comparator an FM signal, and we're comparing it with another FM signal. And by using negative feedback, what we're going to be doing is we're just slowly going to be driving this error term. We're going to be driving it, so it's going to be constantly changing, right? Because this is happening in time. So, at one point in time, we're going to have the input signal, I'll draw it in green, is going to be this frequency, okay? And our comparator, so let's say the blue is originally some sort of low frequency, there's going to be a delta V, there's going to be a difference, a change, okay? So that's going to be passed through our VCO, and we're going to use negative feedback until they're exactly locked with each other.
Yeah, okay.
Right, but the green isn't just staying the same. So it's going to be slowly, so let's say it goes to a lower frequency now. Okay, so suddenly there's not 0 difference between them, but there's a tiny little bit of difference between them. Okay, so now we're again using negative feedback, it's going to change the frequency until we're back into lock.
Yeah.
Does that make sense?
And would that rely on the frequency not changing too quickly?
Perfect. Okay. Yeah, 100%. And that's why we have the low pass filter as well, because when we have two signals that are out of phase with each other, okay, and remember phase and frequency are quite interchangeable things at this point. So if it's a slightly different frequency, the error we're going to get is going to be, always jumping up, jumping down. Like it's not going to be this smooth error, right? I should superimpose these onto each other. If we put them on top of each other, there's going to be, some very low points, some very high points, some points where they're exactly the same. Okay, so that's why we need to smooth this error. As I was pointing to up here, we've got to smooth it so it does become the slowly varying signal. So the message has to be slowly varying, and also we smooth our comparator, so it's slowly varying as well for our VCO. Okay, but this is the last thing, okay, and hopefully this brings it together. Have a look at this signal here. So if we look at the forward path, we've got our message, which goes through a VCO into our comparator. And we've just said that the comparator, this whole phase locked loop system, is going to work such that this input signal here, okay, so the input to the comparators, it's going to use negative feedback to make sure they're exactly the same, right?
Yep.
So what then do you think the input to the VCO is?
Should be approximately the message.
Approximately the message, right? So if we use inverse reasoning, okay, if we know that these are two exactly the same signals, okay, and they're both passing into a VCO, we then know that the inputs to the must be the same. Okay, so in a roundabout manner, we actually get, this is actually our message, the slowly varying filtered errors, right? Because there's always going to be some sort of error unless you just get, a single sine wave, because the sine wave that's inputting to the comparator is slowly changing. So that means the error is slowly changing, which gives us our message back. Does that make sense?
Yep.
Cool. That's my silver bullet explanation. Also, can you tell me when Wasik comes back into the call?
Yeah, he's back.
Oh, has he been back there for a while?
Yeah.
Oh, Wasik, why didn't you say anything? I'm definitely blaming that on you.
No, I didn't want to interrupt. Because I remember that explanation. I wanted to go over it again.
Yeah, right. Well, yeah, I give it to everyone, and it's not the best explanation, but it's a different one. And like the more people who can explain it in different ways, the better, I think. Wasik, do you have a favorite way of explaining a phase locked loop?
Not really. That explanation for me works pretty well.
Okay, yeah, but that explanation was also taught to me by someone who I can't remember, so hopefully you can teach it to everyone else. We can pass it on. So, Wasik, how'd you go with your lab? That went all well?
Oh, that was fine. It was a boring lab.
Yeah, yep. So what are they doing with the lab? Because I did energy. So do you still do the experiments, or how does that work? Is it simulation or?
They give a MATLAB simulation, even though that really doesn't do much, and then they make you watch videos and just design a poster or something.
Yeah. Okay. Cool.
Hold on, I'm demming energy.
Yeah. Okay. How's it from the other side, Ruben? How's it been demoing?
Yeah, I can tell the students aren't really getting much from the things. So
that's hard, because in the in-person labs they were laborious, but they were good. It was cool to be working with actual motors and systems. Anyway, let's keep going on. We've got plenty of stuff to cover. So digital modulation, essentially. So I'll redraw it here, even though we've been through it already. So we have our analog signal. Okay, we sample it. We then quantize it. Okay, and then we code that. So use one of our methods, one of our three methods, either pulse code modulation, delta modulation, differential modulation. We get a string of values, okay? And then from there, we get this bit stream, okay? So 101100 ... okay? And then from here, it's like, well, how do we actually pass that through a channel? Okay? So there's a couple different ways. So what we've been through right now with line codes is what we call baseband modulation, okay? Because we're working with line codes, okay? So that's just like passing it through a wire. Its spectrum is going to be some sort of sync around 0, okay? But what if we want to go wireless with this? Okay, we can't. If we tried to, broadcast two square waves at the same time, they would interfere with each other. Okay, so what we're looking at now is, okay, how can we, in the same way that we did this with amplitude modulation, how can we now shift that spectrum up into a higher frequency? Okay, so, and let's say we had a green bit that we wanted to go as well. So usually they'd be overlapping with each other. But what we could do is we could just transmit it at a different frequency. And that means we can have, two messages transmitted at the same time. Okay, so it's the same ideas we're having from analog, but we're just applying them into the digital sense. Okay, does that make sense so far? Difference between digital modulation and line codes?
Yep.
Cool. Okay, so it's analog, but the key difference is this, is that once we send it over the airwaves, we're going to get back something that looks like this red signal here. So it won't be the same, but instead of being an analog signal where we can't recover that, by resampling this point at, you know, whatever our different points are, usually if our signal noise ratio is good enough, we can actually get back the original data. Okay, so that's the key. Even though we're doing modulation like it is an analog, the key difference is that by using this sampling technique, we can recover our original, or a very, you know, an approximate, a quantized version of our original signal. Okay, and it's very robust to noise. Whereas with analog, anytime you're changing the signal, it's irrecoverable. Okay, so we'll go through three main methods of modulation. So there's amplitude, shift. We call it shift keying. I'm not really sure why we call it shift keying. Do you guys know? Not sure. We have phase and we have frequency. Okay, so let's say I have this, you know, string 0, 1, 0. Ruben, do you have any idea amplitude shift keying, what we'd be doing there?
So it's sort of like amplitude modulation. You send the carrier
Perfect. Great. So
on
essentially
discrete
we're
amplitude,
multiplying it. Okay, so we've got this one carrier here. Okay, and we multiply it by 0, 1, 0. And what that gives us is 0, our carrier, 0. Again, by using a carrier, all we're doing is we're shifting this up into whatever our carrier region is. Okay, and with phase shift keying, what we're doing is we're multiplying it by phase. So we might have our original carrier here. Okay, and then at this point, so we'll draw these points there. At this point, we're going to have a phase reversal. And at that point, we'll also have a phase reversal. Right, so that's phase shift keying. And then frequency shift keying is actually, we're just using two frequencies. So we might have a low frequency, and then we have a high frequency, and then a low frequency. Okay, does that make sense so far? ASK, BSK, FSK?
Yep.
Yeah.
Okay, so it's pretty, it makes sense, pretty stock standard, okay? And the basic idea is what are the bandwidths doing? Okay, so for amplitude shift keying, it's essentially going to be, if we call this section, I'll go up to here, if we call that the bandwidth, okay, by modulating it on, essentially we're getting 2 times the bandwidth, okay, because we're getting those negative frequencies always copied over as well. Phase shift keying is the same, and then frequency shift keying is just like FM. Okay, so it's that same sort of spread, you know, depending on the Bessel function or whatever, because we use it's all like a continuum in frequencies. Does that make sense so far?
Okay, so what the FSK has a whole range of frequencies, not just the 2 frequencies that represent 1 and 0.
Yeah, no, that's a really good point. I think I'm going to retract that last statement, because yeah, right now it should just have these 2 frequencies. I'm not too sure on that one, because in the lecture notes they were saying how there's a continuum of frequencies. So maybe what they're talking about, because in this case we're only using binary symbols, so 0, 1, or 0, but we'll eventually get into Mri signaling. So I'll just write it down here. So instead of binary, we have Mri signaling, where instead of having only 2 states, we can have as many states as we want. So we can have, you know, maybe 4 states.
Yeah.
Okay, so maybe that's where they come with the FM. So I'll put a star on here, and I'll just say look up lecture notes on that one. Okay, to look at the bandwidth, because they were saying how it was the same as frequency modulation, you know, same sort of replications, but yeah, I definitely think it's probably a little bit more complex than that. Great. Okay. And the one thing that they always love asking questions about this is differential encoding. Do we remember what differential encoding is? No idea.
It's where you encode the difference from the predicted signal.
Yep. So we have whatever the signal is and the signal minus 1. Okay, so if we have,
Right.
let's say 1, 1, 0. Okay, we always start with 1, and then we use so as an XOR. So are these two the same? Yes. Okay, so we'll put a 0. Are these two the same? No, we put a 1. Are these two the same? No, we put a 1. Okay, then we pass that through, and either it works, tick, or it doesn't work, box. So if it works, we'll get the same out, 0, 1, 1, 0, 1, 1. Again, we'll look, are these two the same? No, they're different, so we'll have 1, these two the same, different, 1, these two the same. We have 1, 1, 0, okay, so that's the same as that, so that demodulated correctly. And if there's some sort of channel inversion, so we'll get 0, 1, 0, 0. Are these two the same? No, so we have a 1, these two, 1, this is 0. Okay, so you can see it correctly demodulates in both cases. And that's something that we can link differential encoding and these line codes, right? Because in our labs, we realized that some line codes can actually be transmitted successfully, but flipped, okay? And if we had a differential encoding, that flip wouldn't matter, okay? So definitely we've got to consider what encoding we have in terms of how we can change our message signal.
Yeah.
Okay, so differential encoding is one good thing. So Mri signaling. So let's say we have a string 0, 1, 1, 1, 0, 0. Okay, so I'm sure you know how to draw this. So if we just use amplitude shift keying, we'd have 0, 1, so I'll draw 1, 0, 0. But what we could do is we could say, okay, how about we subdivide these into, instead of using binary symbols, using 4 different levels. So we have 0, 0, 0, 1, 1, 0, 1, 1. Okay, and we could encode the 0, 1. We could encode this as one level of amplitude, and 1, 1 we could encode as another level of amplitude, and maybe 0, 0 we encode as a 0 again. Okay, so it could actually represent 2 bits by 1 symbol. Okay, and this is where we get into symbols.
Yep.
And the reason why we call them symbols is that we just want something that can represent data. Okay, and we've got this trade-off because essentially what we're doing, so we're always limited by, what was Shannon's theorem? Ruben, do you remember Shannon's theorem on the channel capacity? It was like
Not
bandwidth
exactly.
log something. I think it was bandwidth log 2 1 plus signal over noise. Okay, so it's just basically it's proportional to whatever the bandwidth is and the signal to noise ratio. Okay, because you might be thinking to yourself, well, what we've done here is the bit rate, okay, of this. So we have 2 terms. So the baud rate is just the number of symbols per second.
Yep.
Okay, so essentially, instead of going from, you had 6 symbols here before when we were in binary, and now we have 3. Okay, so we've halved the baud rate, which means the bit rate, which is the number of bits per second, has increased. So we've doubled it for no apparent cost. But Ruben, why doesn't that hold up? Why don't we do this all the time?
Because the more levels you have, the less of difference there are between the levels.
Perfect.
So
And that increases what?
that increases the likelihood that you'll get noise effects. So it decreases
Noise
the
or-
SNR.
SNR, awesome. Okay, so you can see this Shannon's theorem, the capacity of a channel is related. So the bandwidth and the signal noise ratio are both related. So if you increase the bandwidth, okay, you'll get you can have less signal to noise, but if we decrease the bandwidth by doing something like increasing the baud rate, etc., the channel capacity is fixed, so our signal to noise will suffer as well. Okay, so we can't have our cake and eat it too. Perfect. Okay, so that's the basic reason of MRA signaling. So this is the first type that we look at. The second type is quadrature amplitude modulation. Okay, Wasik, can you remember what this is doing?
Is it where you send two different signals that are completely out of phase with each other?
Perfect. Yep. And why do we do that?
It's to maximize the usage of bandwidth, I think.
Great. Okay. So if let's say we have this bandwidth of the signal, okay, this is in the frequency domain. If we just rotate the phase by 90 degrees, we could have the same bandwidth, so they're occupying the same space, but because their phase is out, we essentially get that bandwidth for free. Okay. Of course, there's going to be costs with that, and I'll get into that just in a moment. But essentially, that's why we do this. And when we say in quadrature, we have these two phases. So I call them phase 1 and phase 2. Okay, so essentially what we'd be doing is we'd be getting one signal. So it might be amplitude modulated. Okay, and getting another signal that's 90 degrees out of phase. And then we could sum them together, so we get some weird signal. But by using coherent detection, okay, so by multiplying that with a sine and multiplying it with a cosine, we can get these original messages out of it, okay? And where that breaks down is by doing that multiplication, we're going to be increasing the signal noise ratio, because we're going to get these small deviations in our signal, because when we get out of phase with each other. So yeah, that's going to increase the susceptibility to noise. Okay, does that make sense so far, what we're doing?
Yeah.
Okay, great. So what we get then is these arrays. Okay, so let's say we had we'll go back from our MRA signaling. So let's say we had a symbol with 2 bits in it. Okay, so there's 4 different levels. So I'll draw this as in the time domain. So we have A2, A1, negative A1, negative A2. Okay, they're just different amplitudes. And let's say we have some sort of, this is our wave here, then it goes up, then it, so I'll draw in red. So this is our signal, okay? And let's say it drops now back to negative. So it's still gonna be the same height, but we'd get a phase reversal. Does that make sense? So it's still the same amplitude, but by multiplying it by negative A2, we're giving it 180 degrees phase reversal. Does that make sense? And if we then went back to A1, okay, we'd have another phase reversal, and it would go back to that amplitude. Does that make sense, how those 4 amplitude levels are relating to our signal? Ruben? Not really?
Makes sense. Wouldn't 180 degrees phase shift mean it goes up to the top level?
Great. Yep. Awesome. Yep. So that's a 90 degrees phase shift. Thanks for pointing that out. So, yep. So it'll be that up, and then it'll go back down, and that 180 degrees would happen at this one as well. Thanks for that. Did I get that right the other time? In terms of, yeah, I'm not sure. 90 degrees versus 180. I'm sure I've I've made a mistake on that before, but yeah, so that'd be a 180 degree phase shift. Thanks for pointing that out. Okay, and then what we have is this array, right? Because we've got all this combination. So we've got on on both axes. So this is our phase 1, our phase 2. Okay, we've got 4 amplitude levels. So we write a little dot. Okay, so there's going to be 4 dots here, 4 dots down there, 4 dots down there. So we have 16 possibilities. Okay, so we could have it at A1 and being on phase 1. We could have A2 being on phase 1. We could have negative A2 being on phase 2. We're going to have all these different combinations all superimposed on each other. Okay, but the reason why we draw dots, okay, because you can see here, even though I've written phase 1 and phase 2, this is a voltage level. So any sort of noise that we have on this it'll make a sort of cloud around these dots. Okay, so instead of, say if this black line, we're supposed to be at this red point here. We're supposed to be at A2, but let's say there was a bit of noise we added. So instead of being A2, it was a little bit above, a little bit below. Okay, and let's say this was on phase 1, so we're up at A2. That means it would be varying a little bit above and a little bit below. Okay, or maybe it's drifting a little bit in and out of phase. Okay, so there's these 2 axes that are going to change the noise around it. It's either going to be drifting out of phase or in amplitude, and that's going to create this ball of noise around these dots. And essentially, once those balls cross over, our channel capacity has been hit. Okay, so we can't fit any more in by either increasing the amp, well, I guess this is one to ask to you, Ruben. Once these balls all hit each other, what could be the 2 things we do to make space back in the balls again? So these 4 points.
You could increase the voltage levels so that the
Perfect
signal noise ratio would be bigger and they're further apart.
Yep. And there's another one, and it's hard to spot, but what we could do is we can add an extra axis. Okay, so we could add a third phase, phase 3. Okay, so what we could do is we could increase the voltage levels, and that means there'd be more space. So as we talked about before, our signal noise ratio, etc., will change. Or we could add another phase, and you're like, oh, well, how do we add another phase? That brings us to the third thing, which is multiple phase shift keying. Okay, so what we do with that is we equally space our phases around. So we have a circle and we equally space these balls around. Okay, and that's so we have one signal here. We have it maybe, so each of these would be 45 degrees out of phase from each other. Okay, so we have a signal here, 45 degrees. Maybe we have a third signal at 90 degrees. And they're all encoding different things, so I should draw them at different frequencies. Okay, and then we all superimpose them into this big crazy signal. And then at the other side, we multiply them by those different carrier tones as well in the different phases. And we should get back our original signals as well. Does that make sense what we're doing there? With,
yeah.
multiple phase shift keying?
I don't know, if you multiply, say, something, a sine wave by a sine wave shifted by 45 degrees, wouldn't we still get something? Like, how do we isolate the original wave without getting the 45-degree copies?
I'm not too sure how to explain that. Yeah, I'm not too sure. I think it just comes back to, I guess, what we learned about coherent detection and detecting 2 quadrature sidebands. I always thought that was just multiplying them by that specific phase. But yeah, I don't think I've got a really good explanation for that.
That's right.
Can you think of anything to explain that or to disprove it?
I'm not fully sure.
Yeah.
This area is just very, very difficult for me to understand. I haven't really gone over it.
How are you going so far with the quadrature amplitude modulation and the phase shift keying?
So up till QAM I was fine, but then the multiple phase shift keying, I'm a bit lost on this, because what I don't understand is that if you have multiple signals which are all about 45 degrees out of phase with each other, would they still not interfere with each other? Because I thought they had to be like 90 degrees out of phase to have no effect on the other signal.
Yeah, but why is that? Why do they have to be 90 out of phase? Because can't we measure anything? So let's say we number these as 100, 110, I think 111. This is an example from the lecture. So let's say 100 is this wave here. Okay, and if we wanted to code maybe 111 next, we'd have a 90 degrees phase reversal. 90 degrees is just back this way, right, Ruben? That's a 90 degrees, I think.
Yeah. I don't know. There's no reason they have to intersect at the same point if you're phase shifting them.
Yeah, because if you had a 45 degrees, it's going to have some sort of jump and then continue on from that.
Yeah, but
Okay,
even 90
and this
degrees
is
could
if,
do that.
Yeah,
Yeah.
great. Okay, so the 9 degrees could jump as well. Okay, so this is if we had symbols that were happening after each other, so they're not superimposed on each other. And then from here, yeah, I'm not really sure how the modulation or demodulation would work. I can have a look through the lecture notes. Actually, oh no, it does have some good stuff here. Yeah, so it says it multiplies them by an in-phase channel and a quadrature channel, and I think with the maths of that, Ruben, it somehow works that out. Because so you multiply it by an in-phase channel, then it passes through a low-pass filter, and then there's some sort of sample that reconstructs it.
Very good.
But yeah, I'm pretty sure maybe if we look back through coherent detection, actually no, yeah, I think it's definitely coherent detection, right? Because if you have two waves like a sine plus a cosine or something, and you multiply both of them by a cosine, you get cos squared and then sine cos, and then if you look at their frequency spectra or something, you get your original, and then there's all these high frequencies, so then you low pass filter them. I'm not quite sure how that maths goes, but I think that's the way you prove it.
Yeah, okay.
Does that make sense? Okay, and so all we'd have to do change here is instead of using a 90 degree phase shift, we'd have a couple of different phases. So one that was 90, one was 45. Yeah, but the very last pages of lecture on the lecture on bandpass modulation, they'll have those slides, but they're pretty, they're pretty sparse. So this actually might be a good one for, I haven't actually looked at the Wikipedia, or maybe there's a YouTube video on multiple phase shift keying.
Okay.
I'm sure and is there a tutorial question on it? That might be able to help as well.
Yep.
I think in Tut 4, the last question. Oh, no, that's yeah, no, I don't think I have any questions on this, but I guess that's just the general overview of it. So trying to use different phase carriers, and then that's why I say MPSK and QAM, both of those you can combine them. Okay, so as we said with these little balls, okay, we can either use multiple phases or we can use multiple amplitudes, and both of those will affect the amount of data we can carry, but there are fundamental limitations with the signal noise ratio versus the bandwidth. Cool. Okay, I think that's it. Do we have any more questions on those two parts? Ruben, Wasik.
Yeah, I think it's fine for now. I'll have to see a few questions for me to properly understand them.
Yeah, I don't think you'll find any questions on it, which I guess is a good thing. That they don't really ask questions about it, but yeah. Okay, and the last thing that we'll cover is transmission, and we have digital noise. So I guess we've only got 20 minutes left. So do we want to cover transmission and digital noise, or do you want to maybe look into the past papers?
I don't mind either ways.
Ruben? Ruben, are you there? I think we lost Ruben for a
Helps
bit.
to unmute. Yeah, I haven't done either of those topics, so it'll be new content for me. I don't know if there's much point to that.
Yeah, okay.
So, yeah.
So maybe, let's maybe
Smash out the past paper.
smash out a past paper. We'll see. You cool with that?
Yeah.
Cool. And we just won't cover. Oh no, Ruben, you've covered that, right? You've covered transmission, like that's with the multiplexing inter-signal interference. You just haven't done the digital noise, right?
Yeah.
Cool. Okay. Give me 5 minutes. Let's go through it. Okay. So basically, transmission. Okay. What are the 3 different types of multiplexing we can have or seek?
First one that comes to mind is TDM.
Yep. Time. That's another thing we could do.
Would it be frequency?
Perfect. Last thing.
Phase.
Phase. Okay. Okay, so time is just when we separate it into different times. Frequency is just doing the same thing in the frequency spectrum. So frequency multiplexing is pretty much the basis of AM communications, right? So we have different bandwidths reserved. Okay, and phases is, as we were saying before, separating a phase into different points. And why do we do multiplexing, Ruben? Like, why is multiplexing? Why is it a thing?
So we can fit maximum signals in the bandwidth.
Yeah.
Because our signals don't require the same bandwidth.
Perfect. Okay, and that's easy to think of in terms of bit rates. So if you're sampling at a low frequency and your channel has a high capacity, you can fit more channels in, and also in the frequency space, right? So if you have a very large bandwidth, you can fit in more channels, which is another reason why we like having high bandwidth systems. Okay, so that's on that. So usually, I think you've been through how to do time. It's like they always have some sort of spinning thing that sort of puts different channels onto one. Okay, and then it's just basic maths with terms of just adding them all up. Information theory, there are questions about this. Okay, so what we have is entropy, H, okay, which is equal. So the sum over all our symbols, so the total, okay, the probability of each symbol, and then also the information, I of j. Again, I of j is just log base 2 on 1 on the probability. So we can rewrite this as the negative sum of the probability of whatever the symbol is, log 2 of the probability again. Okay, and so when I say the probability, so if we had, let's say, a 4-bit system, Ruben, what would be how many possibilities would a 4-bit system have, and what's the probability of each one of those happening?
So 4 bits would have 16 symbols. Like 16 symbols or 16 levels?
Yeah. So it's going to be, so instead of saying 4 bits, sorry, I should say, what would that be? Yeah, I'm not sure, I'm a bit confused now because I'm rushing, but so if we had a 3-bit, it would be 8. Okay, so the probability of each would be 1 on 8. Okay, and you'd have that, let's say we were, having 4 symbols, each would be 3 bits. Okay, so the probability would be just that to the 4. Okay, if we had 4 of those, if we had some sort of message, that was 4 of these symbols all together. Okay, so then if we're looking at the information ij, it's just going to be the log 2 of that. on 1 over pj, okay, which is 8 log 2 of 8 to the 4, and I think it works out to be 12 bits. And if we count these up, it's just 4 times 3, so it's 12 bits. Okay, so we haven't really learnt anything, but this is because we're using things with equal probabilities. Okay, what we could do is we could look through symbols that have different probabilities. So if we had 4 symbols and probability of A was, I think I'm just going through the lecture example, 0.9, it could be 0.05, 0.025 PC. What you do to find I is you do the sum of the probability and then log base 2 of the probability. That's a negative. You do the sum of those, and then for this, I think it adds up to something like 0.61 bits per symbol, okay? So it means, because how do we represent these symbols here? So if we have a symbol that happens, 0.9, so 90% of the time, you could think for here, okay, we use, 2 bits, so we have 0, 0, 0, 1, 1, 0 to encode them all, but we don't have to do that. We could use maybe 0, 1, and 0, 0. Okay, and these will both give us different bit rates, because of course for 0 and 1, we're going to be using less bits, okay? So that is the information theory, the entropy part of that. There was also a section on intersignal interference. Okay, so basically if we have square waves, when they go through whatever our transfer function is of our channel, they can actually overlap to each other. So we have 1, we have 2, and that means if we do the summation of those, we get this third. And if we decode that, we might be missing out on this 0 bit inside there. Okay, and the reason how we can measure that is using I patterns. And so, Wasik, do you know how we generate I patterns? Ruben, do you know how we generate I patterns?
Just looking at the lab, yeah.
Yeah, so you essentially
Gradually increase your frequency until it looks closed.
Yeah. So you pass in a random string, right? So an I pattern is just superimposing all the different values. So read out to me a 3-bit number of your choice. So just 3 bits. Like 0, 0, 0. 101. Okay, so we have 101. Great. Read out another one.
111.
111. Let's say 0, 0, 0, 0, 0, 1, 0, 1, 0. Okay, so we superimpose all the different variations, right, over each other for a long period of time, and they give us what this I pattern is. And if we had more noise on each of those different signals, it would close our I. Okay. Oops. So the height of the I is the noise. Okay. And what's the width of the I, do you think, Ruben? So that'd be if there were different slopes. So what would that be affected by?
The frequency.
Yep. Okay. So this is
Or
amplitude / noise, and then frequency / channel. Okay. So if we had a bad channel, it would affect that. Okay. And those two things affect when we sample. Okay. So that's the screen point here, and also what the thresholds are. Okay. So for any digital system, we always have positive and negative thresholds. Okay. So the timing and the thresholds are determined by those two things. So that's why I patterns are important. And when the I pattern closes, okay, that's when we can't distinguish. So coming back to, if we had a 0, 1, 0 here, and let's say there was a lot of noise on this, and we had a 1, 0, and there was a lot of noise on that, if we took our sampling point here, again, we timed at this point, we might actually get, a 0, 0 or a 1, 1 for those signals, okay? So when the I closes, that's when we know we can't be entirely certain. And that's why we have to run it many times, because noise is random, okay? And the last thing we learned about in this section, so we had entropy, we had information, intersignal interference. The last thing we learnt about here was coding blocks. Okay, Wasik, do you know why we use coding blocks? So that's where we have, you know, instead of 0, 0, we might code that as, yeah, 0, 0. We put these, what we call parity bits. Okay, and the more bits we have, it increases the redundancy. Okay, because if there's errors, we can check it, but it also increases the cost. And that's where it comes to, we draw out these little patterns here where we have a dark circle we put around here. So these are the 4 different possibilities you have if there was 1 bit that changed. Okay, and that increases to 8 if, oh no, if the 2 bits change, and it increases to 8, etc. And that those circles keep going wider and wider. So if you have a bit error, you sort of follow this path until you hit an edge. Okay, and if you have another symbol over here and it overlaps, you can have double ups. Okay, so let's say you had a 0, 0 followed by a bit of 1, 0, 0 or something. You would need, like, let's say maybe 2 or 3 different bit changes. So it might be, you might get 0, 1, 1, 0, 1. Okay, so that's 2 different errors. Sorry. And this comes into the Hamming weight, okay, of whatever the code we have. So the number of parity bits will affect, you know, what we can correctly demodulate or not, okay? And this comes into the Hamming weight. Okay, I don't think we have time to go through it. So look through your lectures, that there's tutorial questions on this. And essentially is how do you generate the code? So if you have your message, you multiply it by this matrix G, which generates your code. And then that code, you then multiply with your H matrix, which gives what we call your syndrome. And that allows you to get your original message back or to check. Okay, does that make sense? Wasik? Sorry, can you hear me or?
Not 100%. Since and error correction is just, yeah, it's left my head for some reason.
Great, don't worry. You'll have the next, like, when's your exam? You've got a week or something to look through.
Yeah, because I remember even last exam there was a question on having distance and all, and
yeah.
it was really bad.
I remember, like, I tried to memorize like the G code and the H code to get the syndrome. It was horrible, but yeah, don't worry. Look through the lecture notes. They have a really good worked example, and there's also tutorial questions on this. Okay, and I don't think we'll have time to go through the past papers, but I'll put them up. They have solutions. The last thing we'll cover is digital noise. Okay, so that's just a lot of theory, but there's 3 main points. Okay, so the first is pulse shaping. Okay, so if we have a square wave, we're going to have a sinc function. Okay, but what's one way we could reduce that bandwidth with Wasik?
But could you repeat that? I didn't hear you.
Yeah, what's one way? How do we shape a pulse? So instead of having a square wave, how we could shape it to decrease the bandwidth? What's something we could do? Or maybe another way of putting it, what would happen if you filtered a square wave? What would it look like?
I would say it would look like a bit like a sync function, because if I remember the filters, they aren't perfect. They have a bit of a roll off. So
Perfect. Yep. So essentially it'd smooth it. So this is the time domain. And in the frequency domain, if we filtered it, it would have a small bandwidth, okay? But instead of filtering, what we do is we do pulse shaping. So pulse shaping is in the time domain. So what we do is we pass these pulses through and they become this shape, and that gives us a smaller bandwidth. But what's the trade-off to that? Ruben, I think we've been through this a bit before.
Yep. Well, you're just cutting down your square wave, and it's going to make your eye smaller, perhaps.
Yep. Perfect. Okay. So
More
there's
susceptible to noise.
yeah, I don't know how to say it. So yeah, so it's both. So it's more susceptible to noise, also more susceptible to timing. So I just say distinction. Do you guys have a better word for that? Like when you have a square, it's very easy to tell where one ends and the other begins. Whereas if you have these shapes and they all add on each other, it's very hard to tell, at what points they should be. Anyway, so I'm just going to say distinction. You know what it means, but so we're trading that between bandwidth. The second thing we look at is matched filters. Okay, so if I pass, let's say I pass a square wave into a filter and I get, some weird shape out, what could be a way of recovering the original square wave if we know what this filter is? Ruben?
Pass it through the reciprocal.
Perfect. Okay, so 1 on H, and we should get out something with our square wave. What's that not going to remove?
Channel noise.
Noise. Perfect. Okay. So that's one method. And then the last thing we learn about is autocorrelation. Do either of you, have you heard of autocorrelation before? Or correlation?
A little bit, yes, but don't really understand it.
Yeah. Okay. So, yep.
Is that how well it relates to the previous values?
Perfect.
Like,
yep.
Does it jump around?
Yep. So if I have any sort of continuous signal, okay, you can see that if I start at this point here, it's obvious that there's a sort of band here that I'm expecting the next signal to be in, right? And then if I start at this signal here, that band shifts, right? But what's a signal that isn't correlated?
Noise.
Noise, okay? So noise doesn't have that. So of course there's a Gaussian distribution of noise, okay? So it is improbable to have higher. But if I gave you a point here, you should statistically be unable to guess. Like you have a region, but you won't be able to guess where the next point could be. It could be very high, it could be very low. It's completely random. So we can use that in terms of our signal. So if we get a signal plus noise on it, we can pass it through an autocorrelation filter. And essentially what that does is it measures it at a point, okay? And it has some sort of memory that it can use to then predict it. And it keeps doing that as well. And that can help to reduce the noise in our system, okay? We've hit 5 o'clock. So what I'll do is I'll just look over. Do we have any final questions before we finish up? I love how if you zoom out on the big page, you can see how small my writing starts and then it gets bigger. So one thing I don't like about whiteboards is that they scale. But yeah, do you have any questions, or what sort of resources are you going to use in these next coming weeks? Or do you want any advice on study in this last minute?
I did have one question.
Yep.
So what's the difference between channel codes and line codes?
Perfect. Yeah. Okay. So line codes, as we said before. So if we have, let's say a wire, right? We can pass down a channel code, a line code, sorry. Okay. And the spectrum of that is going to be centered around 0. But let's say we want to send it, across an antenna. Okay. If we wanted to send, because you can't send 2 line codes down the one line, right? Like you can't send 2 electrical signals at the same time. Okay. But what we can do is we can use some of these multiplexing things. So we can use digital modulation. So this comes to amplitude, phase, or frequency shift keying to send pulses at a certain frequency. And that means we can also send, very high frequency pulses as well. Of different codes and very low frequency of different codes. And what happens is in the frequency domain, they're all going to be multiplexed on different frequencies, so we can fit more in the bandwidth. So those are the two basic ideas. So you can still have, polar, bipolar non-return to zero line code. So we'll draw it here. You can still have this sort of line code. You can still actually digitally modulate that with some sort of carrier wave and send it across the airwaves. Okay, so the digital modulation is just talking about how do we somehow, relate our digital signal to some sort of carrier wave so we can then modulate it onto a higher frequency like we have with like amplitude modulation. And line code is more about, well, how do we get there in the first place? How do we choose what shape of pulses we have? Okay, so usually
that makes sense.
when we're doing, so when we're doing digital modulation, we only focus on, what would it be? Probably either unipolar return to zero or maybe bipolar return to zero in terms of when I was talking about these negative amplitudes. Okay, but yeah, we could definitely implement something like Manchester or bipolar. It's just the shape of the envelope that we'd be changing.
Yeah.
Ruben, did you have any final questions or things that were that you had questions on?
No, not that I can think of.
Cool. Okay, well that finishes up. Sorry, went a bit over time, and sorry, of course, I think it happens everything that I always I struggle getting to the past papers. But for me, they're not as important as the teaching because, you'll have I'll put up the solutions. You'll have those that you can work through, and as long as you have the understanding there, then you can understand what they're doing and why they're doing. So I'll put up, I don't know, in 5 or 10 minutes, I'll put up a feedback form, and then once you complete that, there should be a link to it to a Google Drive. Any final comments or something before I end the call?
Just the one thing. Do you have the past paper for the last semester?
No, I don't. And actually, I don't have the 2019 as well. So I've got 2005, 2006 with solutions, and I've got 2013, 2017, 2018 without solutions. And I think I just got them from, I don't know, ELSOC or the uni library or something. But yeah, if you have the 2019, it'd be great if you can just pop that on the crash course so Ruben and I can access that. But yeah, definitely not the 2020 term 1 version.
Okay.
But that might be a thing. Honestly, I've never done it, but maybe you could reach out to the lecturer and ask for the for a copy or for solutions of past ones. I've never actually done that before, but it's probably worth a shot. Cool. Okay, well, I'll end that there. I've got to get going, but thanks for joining. I had a really enjoyable session. I hope you learned something. Anyone who's watching the recording, please feel to reach out on Teams, if you have any questions about anything. And yeah, good luck for your final exam, and I hope you've enjoyed the course so far.
Thanks, Tim.
Righto. Good on you, Tim.
Okay, well, I guess I'll see you on campus on time.
You also.
Cool. See you, everyone.
See ya.